with our opener, coming up with a definition of polygons. So we're in section 3.1, and we're going to talk about polygons and symmetry. So, our definition, we came up with a really good definition. We said it was, and we call a shape a figure, is what we normally call it. So, a polygon is a figure with, and we came up with a list. It has at least 3 sides. The sides are segments. We said that we had to be in a plane. So polygons are flat. And just a couple of other details. The sides meet at a point called a vertex. And there's one other thing that's important about polygons that we didn't get into, is that the sides meet only 2 other sides. So what that means is we can't have a shape that's like this and then have another side here and say that that's a polygon. So each side only meets 2 other sides at the most. All right, so and we came up with the most of this just talking about our opener. And I just want to draw a quick picture here. I'll draw, whoops, that's not what I want to do. I'll draw a triangle for a polygon, get a solid line here. And it doesn't matter what our polygon looks like. This is a vertex. We can think of the vertex as the corner, and that's a side. So this triangle is an example of a polygon. The vertex is a corner, and and then each side is only meeting 2 other sides. And poly just means many. And gon comes from the word for angle. So if we were being very literal, this polygon would be many angles. But if it has a lot of sides, it also has a lot of angles. So any questions about what a polygon is? I think we all had a pretty good idea already. All right, so next thing we're going to do is talk about how we name polygons. We name them by how many sides they have. And we know a lot of these names already. So let's talk about, let's make a little chart here, side and name. So if our polygon has 3 sides, what's its name? Triangle. We all know that one, right? If it has 4 sides, well, square is a certain kind of polygon. Quadrilateral, there we go. Quad means 4. And this word lateral, we'll use that a lot this year. Lateral just means side. So we'll talk about lateral faces, lateral surfaces. So lateral just means side. A 5-sided polygon, what do we call that? Pentagon. Six sides? Hexagon. 7 can be a little tricky. I'm going to write, Lindsay said septagon. I'm going to write that here. So septagon is one name that we could use for a 7-sided. Anyone know what other name we use? It's actually the official name is heptagon, and the reason it's heptagon is these words, the penta, hexa, and the gon, the word gon, come from the Greek, and hept is the root for 7 in Greek. Septagon actually comes from Latin, so it's just a difference between Greek and Latin. They mean the same thing. How about 8?
Octagon.
Octagon. 9. Does anybody know 9? What did you say, Lindsay? You were close. What did you say? Anybody want to guess? Starts with an N. It's close to ninagon. It's nonagon.
Who got it?
Nonagon. 10?
Octagon.
Decagon.
Oh my gosh. Oh.
So that's like the decimal system. So 10 is decagon. 11 is really boring. Anybody want to guess what 11 is?
A gon.
It is something gone. 11 gone.
Wow.
11 is just 11 gone. 12 has a special name. Anybody know the name for 12? 12-sided figure? It is dodecagon. And dodecahedron, now hedron means, rather than sides, hedron has to do with a solid. So hedron would be a solid shape. And the reason that we give names, the shapes with special names usually have some special properties, or that we use a lot. The dodecagon has some special properties, and most of the higher numbered shapes, higher number side shapes don't have properties that are that interesting. So after 12, then it just gets boring. 13 gone, 14 is a 14 gone, 15 is a 15 gone.
Has there ever been like 100 gone?
Yeah, and I don't know if it has a special name or not.
I heard of like decaquadragon.
So,
like a dice.
right?
Like my math teacher in 8th grade, he'd have these like 34-sided dice.
A 20-sided is a icosagon.
How can you have a 30-sided dice? That's impossible.
All right, so this is just a quick list of how we name them. We name our polygons by how many sides they have. And it's something that we're all fairly familiar with. All right, let's talk about a couple special types of polygons. So there are 3 special types of polygons that we'll end up talking about a fair amount. The first is equiangular. So what would you guess equiangular means?
Equal angles.
Equal angles. All the angles are congruent. So a square would be an equiangular polygon because all the angles are 90 degrees. Equilateral. All the sides. We said lateral means side, so all the sides are congruent. All the sides are the same. There's such a thing as an equilateral triangle, and it is also equiangular. So all the angles in an equilateral triangle are 60 degrees. So it's equilateral and equiangular. And then we have regular. What would you guess regular means? That they have both of those things. Yes, all angles and all sides congruent. So, a regular polygon, okay? A square is a regular polygon. All the sides are the same, and all the angles are the same.
Would a star be?
A star, well, let's look at a star. A star is a polygon. And this is a special kind of polygon, but here we have an angle like so, but here we have this angle. So could this be equiangular?
No.
No, this couldn't be equiangular. But it could be equilateral. The star could be equilateral, but it couldn't be equiangular. So like a stop sign is an octagon. A stop sign would be regular because all the sides are the same shape and all the angles are the same angle. So a square would be an example of a regular polygon. The equilateral triangle that we talked about, that we mentioned, would be a regular polygon. All the sides and all the angles are the same. The ones that we'll talk about the most this year are equilateral polygons and regular polygons because they're nice and they have special things that make them easy to work with. So we know what a polygon is, we know how to name it, we know a few types that are going to be important, and we want to talk about a couple of parts of polygons. And we already know a few. We know what the sides are and we know what a vertex is. But there's one more part, or a couple more parts that are going to be important. So let me draw a polygon and a little more interesting one, and we will talk about the parts. So we have a pentagon, right? So the corners, we said the corners are each a vertex. This point right here is the center. Nothing that different about that. And we said all of these are the sides. Now if I draw an angle from the center to two vertices, the plural of vertex is vertices. If I draw this angle is called the central angle. The central angle is from the center to two corners of the polygon, the two vertices. So the central angle has the center as the vertex of the angle. So the center is the vertex of the angle, and the measure of the central angle and this is going to turn out to be important for what we will talk about, all the different angles in polygons a little later in the chapter, is 360 degrees divided by the number of sides. So it's pretty easy to find the central angle. And this is for a regular polygon. So 360 degrees all the way around. We divide 360 degrees by 5, and we end up with a central angle for a pentagon being 72 degrees. So all we have to do is divide 360 by the number of sides in our polygon, and we can find the measure of this central angle. So these are parts that we're going to talk about a lot with polygons. And the other thing that's important about the center is that the distance from the center to a vertex is the same all the way around the polygon. So the distance from the center to each vertex is congruent, so these segments are congruent.
Is that always the case?
For a regular polygon, that's always the case.
Like what if you just do like one really long line and short, 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 short?
Then that would not be the case. It has to be a regular polygon for that to work.
Well, what would be a regular about that?
Well, so let me get a new page here. So you're saying something like that?
Yeah.
So we can't really talk about a center. So to have a center, we have to have a point in here where that point is the same distance to each corner. So no matter where if we tried to put the center there, it'd be really short distance there, but a really long distance down there. So it really only makes sense to talk about the center of a regular polygon. So everything's equal, everything's the same. And we'll talk about symmetry in just a second. Everything has a nice.
Is that using
nice.
Polygons?
Yeah, it has. What do we have? 5 sides. They're just not all the same. So this would be an odd kind of polygon. I think it looks like a bucket pouring water. So anyway, all right. So for a regular polygon, and that's what we're talking about here. Regular polygon, central angle 360 divided by the number of sides, and the distance from the center to each vertex is congruent. So all of these distances, if we drew from the center to the vertex, would be congruent. Excuse me. All right. Last couple of things, really easy things to talk about is symmetry, and it's again something that we all are pretty familiar with. So we're going to, the first kind of symmetry is reflectional symmetry. And reflectional symmetry just means that when we reflect it across a line, after we reflect across a line, the image and the original are the same. We're almost done, so just hang on just a little bit. So when we reflect across a line, the image and the original are the same. The line is called the axis of symmetry. So let's draw a couple of figures that have reflectional symmetry. So here is one. And I'm going to draw my axis of symmetry. Let me draw that a little better. Try one more time. Well, that made it worse. I'm going to start here and I'll do this. About as good as I can get. So this is my axis. So this triangle would have reflectional symmetry because if I reflect it across this axis of symmetry, it's exactly the same. So I'm cutting the triangle in half with the axis of symmetry. When I reflect it across that line, it's the same on either side. If I drew an X here, like so, let me see if I can draw a nice X. So this X would have reflectional symmetry if I made the axis right through the center here, or if I made the axis right here. If I reflect the X across either one of those dotted red lines, it's going to be the same. So this would have reflectional symmetry. If I made a strange looking shape like this, and if I drew this perfectly, you have to use your imagination a little bit here. And if I reflect this right across this line, or right across this line, this would have reflectional symmetry if I reflected across either of those dotted lines. But if I reflected a shape like this across this line, it would not have reflectional symmetry because it wouldn't be the same. So this would be a no. So our test for reflectional symmetry is fold on the axis and see if the picture is the same. So if we can fold along our axis and the picture looks the same on either side, then we would have reflectional symmetry. So all of these shapes would have reflectional symmetry, and this one would not. Now, would this triangle have more than this axis of symmetry? Could I put an axis of symmetry somewhere else on that triangle for it to have reflectional symmetry?
Yeah.
Where would I put it, Preston? What do you think? So where does this axis go? Through a vertex and straight through the middle of the other side?
You can put it on the bottom line.
Couldn't I put it this way?
No.
If I folded the triangle this way, would it be the same?
No.
You don't think so?
Measures are off.
No, it's equal.
It was supposed to be an equilateral triangle, so if I drew it perfectly, it would still work. How about this one? So this one would have three axes of symmetry. This one has 2. This one has 2. This one doesn't have reflectional symmetry. All right, last thing. Rotational symmetry. Whoops. So rotational symmetry just means, listen up guys, rotational symmetry means that the figure can be rotated to match the original. So let me draw a picture that has, or draw a figure that has rotational symmetry. All right, so here's my star. If I start here, I can rotate it once and get to there, and it would look exactly the same. I could rotate it twice and get to here, guys. Get to here, and it would be exactly the same. I could rotate it here 3 times, and it would still look exactly the same. I could rotate it 4 times to get to there, and it would be exactly the same. And finally, I can rotate it a 5th time and get back to the original. We say this has 5-fold symmetry. The letter I, if I draw a capital I can rotate it once to there and twice back to the original. So this would be 2-fold symmetry. And if I could draw see if I can do a decent job of drawing a shape like this, if I drew it perfectly, would have 3-fold symmetry. So rotational symmetry just means, can I rotate the shape around and get something that looks exactly the same? And the number, we call the number of times we rotate, that's how many folds of symmetry it has. So the star has 5-fold symmetry. This capital letter I has 2-fold symmetry. This flower, if I drew it perfectly, would have 3-fold symmetry. So we just count the number of times we have to rotate to get back to the original. If we have to rotate it all the way around, then we say it doesn't have rotational symmetry. The other way we can say that is, and it's not that important, but just so you know, is it's called degenerate symmetry. Or the only symmetry is if you rotate it all the way around. So anything has, if you rotate it 360 degrees, it's going to match the original because you're just back to where you started. All right, so we know what a polygon is. We know we name it by the number of sides. We know different parts of polygons. We know different types, and now we know different types of symmetry. And we'll use all of these to describe polygons as we work through the chapter. So any questions today? All right, the homework. I think you'll find the homework pretty easy. Page 143. Through 58 even. All right.